Hello. In the last lecture, I introduced the basic framework for hypothesis testing. And at the end of the last lecture and today, we are going to study three different ways to make the decision, or three different ways to present the results of hypothesis testing. So one is p-value, another is T-Statistic Approach, and finally, the critical value approach. I explained the p-value approach in the last lecture. The basic idea is, so p-value, what we are going to do here is, so basically we have a hypothesis about the population mean, which is the true mean, the truth, and we believe the true mean is a certain value. And on the other hand, from the observations, we have the sample mean, sample average. And we are going to compare our belief about the true mean and our observed sample mean. If they are similar to each other, then there is no problem. They are consistent. However, if they are different, then one of them may be wrong. So we are going to take the difference between x bar, the sample average, and mu zero, which is the value of the true mean you believe in your hypothesis. So their difference is then standard deviation divided by the square root of sample size is the standard error of for this x bar, and we will denote it as t. T statistic is this guy. So this is the standardized difference between your belief and your observation. And also the reason why we standardize the difference is because we know that this T statistic follows the standard normal distribution. So this is the standard normal distribution. So we can calculate the probability distribution about this guy. If under the assumption that your belief is true, if your belief is correct, then T follows the standard normal distribution. So you can calculate the probability, or we are going to calculate this p-value. P-value is the probability smaller than minus t or greater than plus t. Here is a typo. I have to put another absolute value here. So this is the p-value, which is the probability outside of plus minus t statistic. So that is, this probability is the probability of the possible outcomes that are more different from your belief, right? So in other words, I interpret it as p-value is the ranking of the suspiciousness, right? Ranking, if you rank outcomes from the most suspicious or the most different from your hypothesis to the least different from your hypothesis, then your outcome is at a certain ranking. So p-value is the ranking. So if, for example, if your p-value is, say, 10%, that means your outcome is top 10%, within the top 10% in this spectrum. So that's my interpretation of the p-value. And then we are going to reject the very top, a certain percent on the top, at the top. So if the p-value is smaller than the cutoff alpha, which is the significance level, if the p-value is smaller than alpha, then you are going to reject. So top certain percentage is rejected, and the others are not rejected. So remember, on the top is the most different from the null hypothesis. So you are going to reject, like say 5% of the top 5% most different outcomes from the hypothesis. So that's what I explained in the last lecture. And today we are going to study the T-Statistic Approach, which in the end should be equivalent to the p-value approach. This is just a different way of presentation. So back to the p-value approach, we took 3 steps to calculate the p-value. But what we are doing here is, so we calculated the p-value and then make the decision based on the p-value. But instead of doing this step, we are going to delete the 3rd step, but we are going to make a decision rule directly on the t-statistic, right? So we are going to define the t-statistic in the same way, but and then we will make the decision rule based on the t-statistic. So remember, the t-statistic is the standardized difference between your hypothesis and your data. So the larger the t-statistic is, the more inconsistent your belief is with the data, right? So I will consider decision rule like this. We are going to reject our hypothesis if the absolute value of the difference is greater than a cutoff A. A is a cutoff to be determined. A is a cutoff, and if the standardized difference is larger than that point, then we are going to reject. Your belief is too much different from the data. Otherwise, if the difference is within plus minus A, within the certain margin, then you do not need to reject your hypothesis. This will be our decision rule. But here we have to determine how to choose this value. What is the cutoff? The cutoff should be chosen so that this decision rule is equivalent to the decision rule for the p-value. That is how we determine A. So remember what we considered is, with the p-value approach, in the p-value approach, we were going to reject top alpha probability outcomes. Say, I will simply say 5%. So we are going to reject top 5% outcomes in the p-value approach when the significance level is 5%, for example. And that means, so top 5% means there are positive, so there are two tails. There are large values on the positive tail. Also, there are large values on the negative side. So top 5% is the mix of positive side 2.5% and negative side 2.5%. So you have to keep this in mind. When you reject the most different outcomes, the most different includes top alpha over 2% and bottom alpha over 2%. So both top and bottom are rejected. So you have to choose the threshold A such that it equals the top alpha over 2 probability. So we are going to reject 2.5% from the top and 2.5% from the bottom. That's what we are going to do. That's how we are going to choose A, and we know that that is denoted as Z alpha over 2. So again, we use alpha over 2, not alpha itself, in this subscript. So you have to find top alpha over 2 probability value. And finally, the decision rule for the t-statistic is like this. If the standardized difference is greater than Z alpha over 2, then you are going to reject the null hypothesis. Otherwise, not. Graphically, on the graph, it's simple. This is the standard normal distribution, bell curve, and we are going to reject 5%, for example, 5%. Then you have to reject bottom 2.5%, top 2.5%. So the cutoff level will be, the cutoff point will be these 2 points. These 2 points will be 1.96 and minus 1.96, which is the common value, the values we have used many times before, and again we use them again. Okay, so that is the T-statistic approach. And finally, let me just double check if they're equivalent. Yes, they are, because suppose that so these are two decision rules. First one is based on the p-value, excuse me, and the second one is based on the T-statistic. So I will consider this way: if if T-statistic is on the border, on the boundary, exactly equals, then the p-value, when the second inequality holds as an equality, then the first inequality will hold as an equality. Like if T-statistic equals z alpha over 2, then if T equals this guy, then you are going to get p-value equals alpha. So two decision rules are satisfied as equalities at the same time, so they are equivalent, right? So it's a simple derivation. And then why do we use the T-statistic? Because it's also simple. It depends on to calculate the T-statistic, you need to know the hypothesis and the data and the sample size and the standard deviation. So your hypothesis, the sample mean, sample size, and sample standard deviation. So which are basically from the data or from the hypothesis. What you do not need is the significance level. So it does not need a significance level. So a computer in a statistical program, it just calculates the difference. Then it is your decision to make. And many people who are familiar with statistics knows like 1.96 or approximately plus minus 2 is the threshold for 5% significance level. So make the decision based on the calculated T-statistic is as easy as the p-value approach. So almost all the time a test result comes with T-statistic and p-value at the same time. So these two are the most basic ways to present the test result. Okay, I'm going to explain the next before finishing the lecture. Those are the common thresholds, cutoff levels. So 10%, 5%, 1% are again the common values, common significance levels, and then corresponding to them are those common numbers. We have used the same numbers for the confidence intervals. We use them again for the same reason, for the same rationale. They are kind of parallel. So, and you can find them from the standard normal distribution calculator. So it's up to you, but and I believe you are going to get familiar with these numbers at the end of the semester. And if you take another statistics course, you are going to see them again and again, right? So get used to them. So the next approach is the critical value approach, which is slightly different from the previous two approaches. So I'm going to explain the critical value approach in the next video. Let's see you there.